We saw last time how we could do multi-dimensional interpolation if we have data that was stored on a regular grid. In the real world, however, often that isn't the case. For example, in this plot here we have a map of toxic chemical releases in the Toronto area over a certain period of time. Each of the circles represents the magnitude of the spill, and one can assume that the chemicals were distributed in some kind of fashion around the point at which they were released, maybe uniformly, maybe not. But the question then arises is, how can we take this information here in two-dimensional and in two dimensions interpolate so that we can estimate the levels of the chemicals anywhere else in this area? That's the problem that we're going to look at today, very briefly. So let's assume we've got a set of two-dimensional points, x, and each one of these points has a coordinate xi, yi, and at each point there's a function value fi that we're trying to interpolate, and that might be concentration of chemical, it might be wind speed, it might be a whole bunch of different things. What we would like to do is to interpolate the function value to the red point, which has coordinates x and y. So this point here has coordinates x and y. The way in which we're going to do that is to define a weight function, w. And this weight function is going to only be a function of the distance between the point xy and each of the other points. So there'll be a distance between each of these data points. The kinds of function we might be able to use are, for example, a Gaussian. So w of r is equal to the exponential of negative r squared on alpha squared, where alpha is related to the standard deviation of the Gaussian and effectively determines how steep or how sharp the Gaussian is. There's a method known as Shepard's method, where the kernel is equal to the function is equal to the radius divided by some kind of smoothing length h, and all of that is raised to the power of negative n. So we can see already that this one is singular when the radius is equal to 0. Or various kinds of polynomials. In this particular example here, we have that the polynomial is equal to this polynomial provided that naught is less than r is less than h. Again, h is some kind of smoothing length. And the weighting function w is equal to 0 when the radius is bigger than h. And there's actually very, very many other possibilities. So we need to first of all define the distance between the point xy and the data point xi, yi, and that's just given by the Euclidean distance, which is the square root of x minus xi squared plus y minus yi squared. That's a very easy thing to determine. What we would like to do is assume that data points, the xi, yi, that are close to the point where we're trying to interpolate, xy, are going to influence the data value more than points that are distant. So we have this kernel, and the kernel typically is big when r is equal to 0 and small when r is large. Perhaps we could weight our data values, our fi, using our weight function w. So perhaps we could say the interpolated value at the point xy is equal to the sum over all of our data points, that's sum over I, of the function values at each point multiplied by the distance between our interpolation point and the data points. And obviously, when w is big, f will contribute more. When w is small, f will contribute less. However, there's a problem with this. If our data points are not uniformly distributed, this gives the potential for, first of all, large interpolated values in regions which have a high data point density. In other words, if there's a lot of points close to our interpolation point, this formula here will always give a bigger value, even if the individual function values are quite small. Likewise, it potentially will give small interpolated values in regions where the data point density is low. So in other words, if there aren't many points nearby, this formula here may not give a true estimate of the function value there. So how do we overcome this problem? Well, The question is, how can we determine the number density at a location? How do we know whether there's a lot of points contributing or only a few points contributing? There's quite a simple way to do that. We can use our kernel, our weighting function, with data values equal to 1. In other words, we calculate the number density using this formula here. So n is just equal to the sum of our weighting function based on the distance between x, y, and each of the points individually. This tells us whether there's a lot of points nearby or only a few points nearby. Then, the interpolated value of our function is given by the sum of the data values, weighted by the weight function, divided by the number density. That is, the sum that we had on the previous page is weighted by this thing here. So, this means then that a reasonable interpolated value, f of x and y, is equal to the sum over all of our data points. The first sum, the top sum up here, is the function values multiplied by the kernel, and the sum down here is just the sum of the kernel values. So it's one sum divided by another sum. Note that W of r for a Gaussian, and indeed for Shepard's method, is never 0. It requires that every point that we have contributes to every interpolation, and this is pretty expensive, or can be pretty expensive if we have a lot of data points. So I accidentally mentioned previously, weight functions are also called kernels, so I might use the expression kernel and weight function interchangeably. Kernels with compact support only include points that are close to x and y. So for example, we have, that's our point xy, the red point in the middle there, and we say that we have some kind of smoothing length h. We say we're only going to consider points that are inside a distance h, and so that circle centered on h is what's known as the support for our kernel. And our kernel will look something like that, where it's 0 at the outside and large at the center. So any points that fall within this, these are the blue points, they contribute to the interpolated value at our center point. Any black points that are outside do not contribute. Okay, so that polynomial kernel that I mentioned a couple of slides ago is an example where we have compact support. One question remains, however, and that is, how do we choose our smoothing length h? There is no hard and fast rule. You don't want to choose h too big, otherwise you include all of your points. You don't want to choose h too small, otherwise you don't include any of your points. As a rule of thumb, at least in 2 dimensions, you want approximately 20 points inside your support zone. That will give you a reasonable interpolation. So this is the fundamentals of interpolating from scattered data in 2 dimensions. You can do exactly the same kind of thing in 3 dimensions and higher. Obviously, things just get a little bit more complex in terms of the calculation of which points are close by and which are not.